Right, good afternoon and welcome to the intriguingly titled, Is it a car? Is it a computer? No, it's the Raspberry Pi Java Carputer. So let's have a quick show of hands here. Who here has heard of the Raspberry Pi? Okay, good. I would be very disappointed if there were people who hadn't. Who's got a Raspberry Pi? Okay. And who's got a car? Right, most people. Good. We have the right audience then. What I'm going to talk about this afternoon is a project that I've kind of been working on for the last few months, probably about 6 months or so. And I have no idea where I came up with the idea for this, but suddenly I decided to put a Raspberry Pi in my car and to do some interesting things with it. And this is really the results of that basic idea. Now, as an Oracle employee, I have to put up the obligatory legal slide. And I was just looking at this just before the presentation, and I thought, the following is intended to outline our general product direction. I suspect not. So, anyway, do not be afraid. Do not be afraid of this. In terms of the agenda, I want to talk a little bit to start with about cars and computers in general, because the way that cars work now has become more and more computing focused. There's lots and lots of things going on in cars which require computers. And so I just wanted to talk a little bit about the background of that. I'll talk briefly about the Raspberry Pi. Obviously, you've all heard about it. Many of you got Raspberry Pi, but it's worth spending just a few moments covering the basics of what it is and how it fits into what I've done. And then we'll talk a bit about embedded Java and JavaFX in particular, and how that works with the Raspberry Pi, again related to the project. And the main part of the presentation is going to be covering what I've done with putting the Raspberry Pi in the car. You can see this box at the front here, which is the device which fits in the car, kind of. And then at the end, I'm going to show you some demos. You may notice there is no car here. So the demos are going to be, well, I've got a video that I'll show you, and then I'm also going to show you what we can do in terms of without the car. I'll leave it at that because it'll spoil the surprise. Let's start with cars and computers. Obviously, most people here, almost everybody, has a car, so you're familiar with the concept of a car. Here is a picture of my first car, the Mini Clubman 1000. Anybody here have an old Mini at any time? A few people driven a Mini? Okay, a couple of people. Lovely car, invented by Sir Alec Isigonis way, way back, and very simple in terms of the technology. It was designed to be simple, it was designed to be maintainable. And so I had this car when I was 17 years old, and I had a set of spanners, and so being a mechanically minded person, I used the spanners and I took the car apart, and then I put it back together again and hoped that it would work. But the interesting thing about this is that it had no electronics whatsoever. Well, if you didn't count the radio that I had in there. But from the point of view of the car itself, no electronics. There were some electrics, which obviously controlled things like the starter motor and the lights and things like that. But it was essentially purely electromechanical. So it had these things called points. Let's test the age of the audience here. Who remembers a feeler gauge? Okay, a few people having to set the points in your car, yes. And a distributor. Now, cars nowadays don't have anything like this. It also had a carburetor, which had a manual choke. So that, again, I'm sure not many people here remember the idea of a manual choke, where you would actually have to pull this thing out in order to get the car started, and then you have to remember to put it back in again as you're driving, otherwise you use a lot more fuel. But anyway, it had drum brakes. Now, almost no cars nowadays have drum brakes. It didn't even have an alternator. It had a dynamo to actually charge up the battery. And then it had a few luxury items. It had lights. It had a horn. It had wipers, which would work some of the time. It had a fan inside, which would blow warm air, in theory, over the driver. And it had an ignition switch. And that was basically what you had. Now, my wife gets really annoyed at me because I keep things. I'm a kind of a hoarder. And so when it came to put this together, I found I still had the Haynes manual for my first car. So who remembers Haynes manuals? Oh, reasonable number of people. And so I thought, right, I'll photocopy or copy the wiring diagram for my car. Now, this looks fairly complicated, but it's not. It's actually very, very simple, because literally each item has a wire that goes from it to whatever control is necessary. So if you've got a light switch, the switch has a wire that goes to the light goes to the battery goes to the switch, and that's it. All the other items are wired up similarly. Let's move on a few years, and here's a picture of my current car. It's a slightly more modern car, and it has lots of electronics in it. So if you look at the basic ideas, now you don't have a carburetor, you don't have a manual choke. Now there's a thing called the engine control unit, which is essentially a computer which decides what is the position of the throttle, what is the engine load, how much fuel to inject, what the air pressure is coming in, what the air temperature is coming in, all those sorts of things. And that's what decides how to actually inject the fuel into your engine, how to make the car go. Similarly, it has fuel injection, it has electronic timing, so you don't need to worry about points and feeler gauges or anything like that anymore. The throttle, and this will be the same for pretty much everybody's car, is fly-by-wire, which means there's no mechanical connection between the pedal that you press to make the car go and the engine itself. It's simply a potentiometer which measures resistance, and as you press the pedal down, that sends a signal to the engine control unit, and that helps it decide what to actually put into the engine in terms of fuel. The brakes are a lot more sophisticated. It has anti-lock braking system, so it can monitor the speed of each wheel. If the front wheels stop moving and the back wheels are still going, then it releases the brake slightly, and you get this juddering effect as it allows you to steer at the same time as driving. You know, these are very common things that cars have nowadays. It has an electronic stability program, so that it will activate brakes on different wheels depending on how fast you're driving and how out of control you are. I did like, one of my friends has got a BMW, and he pointed out that in the instruction book, he was one of the few people who read the instruction book, it said, be aware that the electronic stability program cannot defy the laws of physics. Which is quite true. It cannot defy the laws of physics, as I found out one time. My car has a thing called magnetorheological suspension. Quite a long word, but what that effectively means is that the shock absorbers on the car are filled with a fluid which has lots of, well, basically iron filings in it, so that it can be changed in terms of its viscosity by an electromagnet. So there's an electromagnet wrapped around the shock absorber, and then you've got a button in the car which sets it between comfort mode and sport mode, which basically means the difference between comfort mode and uncomfortable mode. But that's an interesting thing, because that gets used a lot in other places. And aside from the other things that you've got, like satellite navigation, and it's got auto-sensing wipers and lights and things like that. Now, this is a reasonable car, but if you look at what designers are doing with cars nowadays, the capabilities that they have in terms of using electronics to control the mechanical side of things is really phenomenally impressive. So, for example, Porsche have a system in some of their higher-end cars where the engine mounts are actually the same as the shock absorbers in my car, where they have this magnetic fluid. As you're going around a corner, to reduce the amount of weight that's shifted as the engine moves slightly on the engine mounts, they actually firm up the engine mounts by using an electromagnet to reduce the shift of weight. That's a very small amount of weight to shift, or a small amount of movement in terms of the weight that's being shifted. Ferrari have another interesting system where on some of the, again, the sort of higher-end cars that they've built, when you go to change gear, you use the flappy paddle gearbox, and you say, okay, I want to change up. So you change up gear or change down. And the computer in the car says, you're changing gear. That's going to put more force through the wheels, which is going to cause a shift in the weight distribution. So we'll firm up the rear suspension in preparation for the fact you're changing gear. So there's these kinds of things. Another example, one more example. Range Rover, the new Range Rover Sport, now has the ability to disconnect the anti-roll bars electronically as you go round on very rough roads so that it can give you better sort of control and things like that. So there's all sorts of things that can be done by combining electronics and mechanics. Now, clearly this leads to a little bit of a problem because lots and lots of electronics means that if you wired everything up in the same way that we did with the Mini, you'd end up with an incredibly complicated wiring system. So to get around that, what the designers do is they use the kind of approach that we've known about for a long time, which is a bus architecture. So now you just have a set of wires that goes from device to device, and rather than wiring them up individually, they form a loop, and then you can send messages on the bus. And so this is a thing called the CAN bus, which is used primarily in cars, but it's also now used in other forms of industrial automation. So in the case of the Audi, you've got 3 different buses. So you can isolate the signals moving around the car. So you've got one which is the convenience bus, which is things like wipers and the horn and stuff like that. You've got the infotainment bus, which controls the satellite navigation, the radio, the, well, I would say CD player if I had one. And then the powertrain bus, which controls the throttle position or takes the information of the throttle position, the engine control unit, and so on. And then you've got gateways between those so that the messages can be routed as appropriate. Being a bus architecture, there's a bunch of protocols that have been defined for this. The most important one really is what's called the EOBD2 sort of setup, and that's the onboard diagnostics protocol. And that's really the way that if you look under the dashboard in your car, you'll find there's a little sort of socket where you can plug things in. And if you take your car to the garage will plug in a device to that, and they'll be able to read information about what your car's been doing. If it's had problems, it may record information about errors that have occurred, and then they can determine what they need to do in terms of servicing. On top of that, there's various different sort of higher level protocols that get used. So there's things like SAE J1850. Not quite sure what that is, but it's a protocol that gets used. Then there's also various other things, and the most important one for what I was doing is this ISO 15765, which is the CAN bus. And so you can get all sorts of information from the car. It's literally you can read, the position of an electric window in terms of the percentage that it is up or down. You can get the position of the throttle, you can get what speed the wipers are going at, things like that. And of course, it's not just a read bus, you can also write, if you're brave. And so what you can do is you can send signals and you can say, okay, I want to set the window to be at this particular position, or I can want to set the brakes to be on, or the engine to stop, or something like that. And there's a lot of possibilities in this. And in fact, there was a good example I saw. There was a sort of YouTube video where somebody had basically hacked their system, and they were driving a Toyota Prius, which had the automatic parking system, and the automatic parking system was obviously able to control the steering with a motor. And so they had a Nintendo Game Boy, they were sitting in the car, and they could actually drive the car using the Nintendo Game Boy. It's a little bit worrying. So let's talk briefly about the Raspberry Pi and where this came from, because the Raspberry Pi is a really fun device, but the ideas behind it are a little bit more serious. Now, I'm from the UK, and in the UK, there's a few things. Anybody here remember the BBC Micro? Okay, a few people, good, good. Way back in like about 1981, the BBC, British Broadcasting Corporation, launched a program called Micro Live. What they wanted to do was to teach people about computers. Now, this was in the very early days of computing, even before the launch of the IBM PC. And back in those days, the idea of a personal computer was something like, for those of you who can remember, a TRS-80. Okay, a few people. Or a Commodore PET. Yes, lovely computers. And so they created this program to help people understand about computing. They wanted to teach them about how to program. Part of that was to create a personal computer that could be used in conjunction with the program, and that's where the BBC Micro came from. Much later, sort of like in 2006, a number of academics in the UK got together because they were concerned about the way that we teach children at school computing. Now, I have a son who's at school, he's 7 years old, and one of the subjects he studies is ICT, Information and Communication Technology. Now, you would think that that would be a great subject to study and that he would learn all about computing and how to program and how computers work. No. What he gets to learn, and even as he gets older, is how to use things like word processors, how to use PowerPoint. Now, that's a really good skill to have in computing, isn't it? Well, I suppose it is, actually, but he learns those kinds of things. If he's really lucky, he will get to learn how to program in HTML. Now, last time we looked, HTML is not a programming language. But you get the idea. They're not really teaching children about computing. And so the academics wanted to change the syllabus and get children excited about computing again, like we did back in the 1980s when I was at school and we learnt computing using the BBC Micro, using the TRS-80 and so on. And so they came up with the idea of creating a small, cheap computer that could be given to children, they could play with it, they could understand what the computer actually did. They could get to program it, they could get to connect it to things, all those sorts of ideas. And that's where the Raspberry Pi came from. So it is a cheap board which has the ability to do programming, it has the ability to connect to things, and it was launched on February the 29th last year, and literally from then over 1 million boards have been shipped. And it's actually proved more sort of popular with hobbyists rather than schools at the moment. But there are a lot of things going on in terms of education around the Raspberry Pi, and that was really the idea behind it. So if you look at the Raspberry Pi specification, certainly if you were in the keynote this morning, and Richard talked about the comparison of the processing power, what you've got is an ARM11 core running at 700 megahertz. Now, you can overclock that up to 1 gigahertz now without invalidating the warranty. But it's certainly not hugely powerful by modern standards. It has half a gigabyte of memory, which is actually, it's not too bad. If you think about how much memory we had in laptops and PCs even a few years ago, that's a pretty reasonable amount of memory. It has various sort of I/O facilities. So the idea is to make it cheap and easy for people to use it as a computer. So rather than having to buy a monitor, you can plug it into a TV using HDMI. You can use the composite video if you haven't got HDMI. It's got audio out through a standard jack plug. It's got 2 USB ports so you can plug things in. It's got Ethernet, and it's got some header pins. The header pins are the interesting thing, because that gives you GPIO, it gives you I2C, it gives you SPI, UART for serial communication, and so on. The other thing is that in terms of storage, it uses an SD card. So again, very, very cheap to get an SD card and plug it in. Now, using that for a Carputer, you have to look at, well, what are the advantages of that in terms of using that kind of board? Well, the first thing is it actually has plenty of computing power. So running at, I run them at about 900 megahertz. That seems to be fine. You can certainly do all the processing you need to do of data and store stuff and do whatever needs to be done. And don't find any limitation in terms of processing. It's also got low power consumption electrically. And that's very good because you don't have to have one of these big boxes that you have in your desktop machine, which has to provide 5 volts and 12 volts and have a big fan in it. So you can power it off the car system. It uses less than 1 amp at 5 volts, so you can actually run it quite happily without draining the battery. There's no problem with that. Persistent storage, as I said, was SD card, and again, that's good for a car environment because if you've got a disk drive, jiggling it about and moving it about as the car moves is not going to be ideal. So SD card, no moving parts, so that's good for that sort of environment as well. The other thing is that Oracle have kind of chosen the Raspberry Pi as a supported platform for embedded Java. And that means that we've done a lot of work around tuning Java for using the floating point processor that's available in the Raspberry Pi. We've done things in terms of making JavaFX run well on it using the graphics processor that's available. We ported Prism to it. We've done all of that kind of work. So it's a good platform for using Java. So let's talk a little bit about embedded Java and JavaFX. So one of the things with Java is that it's more than just one thing. And so we have this idea of different kind of platforms which fit into different kind of environments. So you've obviously got Java EE on the server side, Java SE, which covers sort of the middle range of things, desktops, laptops, but also embedded devices as well. We've decided that Java SE is a good thing for, let's say, slightly bigger embedded devices. If you've got more than sort of 10 megabytes of memory available, which a lot of devices do have, then Java SE embedded is going to work well in that environment. If you're looking at smaller devices, much more tiny embedded devices, then you can use Java ME that will go right down to just under 1 megabyte of memory in terms of actually getting the whole environment to work. And then if you want to go right down into the really, really tiny world, then Java Card will run in literally a few kilobytes of memory. What we've done is to produce two versions of Java for embedded applications. There's Java ME embedded and Java SE embedded. Most people associate Java ME with the work we used to do with mobile phones, but it's now shifted emphasis because obviously we don't really do a lot with mobile phones, so we're looking very much at embedded types of devices. It uses what's called the Connected Limited Device Configuration 1.1. That basically defines the virtual machine that we use and also the basic set of libraries that are available for that. One of the nice things with the more recent versions of ME Embedded is that we have this device access API. And what that allows you to do is to talk to all of these pins that you've got on the board of the Raspberry Pi. So you can control GPIO, you can control the UART, I2C, SPI through a standard API. And that makes life very easy. There's also some additional profiles you can use, so you can put things on top of Java ME Embedded if you want to support different types of things like Bluetooth, for example, and that kind of thing. From Java SE 8 Embedded, there is now there has been an early access of this available for quite a while. As I said, this was tuned for the Raspberry Pi, so we've taken advantage of the fact that the Raspberry Pi has hardware floating point support. By default, the ARM v6 architecture doesn't have hardware floating point acceleration, but we've actually been able to use that because it's there. We've put JavaFX on there, as I said. We ported the necessary graphics processing side of things, made that available. Because it's Java SE embedded, you can use the compact profiles that are defined as part of Java SE 8, and that way you can reduce the size of the footprint for your application and your implementation. What we've recently done, literally in sort of last probably 6 to 8 weeks, is we've now brought the ARM port of Java SE 8 embedded into the standard builds that we do. So when we come up with a new build of Java SE 8, we also come up with a new build that will run on the Raspberry Pi. That's quite nice because as bugs are fixed, undocumented features are fixed, then obviously we can take advantage of that. A little bit about JavaFX on embedded devices. From the point of view of using it, most of it is exactly the same as if you've used JavaFX on top of like your laptop or your desktop. A couple of things which are not supported directly at the moment. So one of those is the web view component. I know if you were in the keynote this morning, Richard said that they had actually got a port they'd done for the Duke pad. That's not part of the standard build that you can get from our website at the moment. I figured that was probably not too much of a problem for my Carputer. Then we also don't have direct media playback. Although the Raspberry Pi is very good in terms of handling media and the capabilities that it has, linking that in with JavaFX and the way that we handle the frame buffer is a bit complicated. So there is a way of doing that, again, in the demos this morning. What we do is basically put a translucent layer from JavaFX on top of the native video player, and then you can get the video to play in your application. But again, I thought for the Carputer, probably not going to be too much of an issue in terms of getting the functionality that I wanted with that. The other thing to remember is resource constraints, because you don't have as much memory as you do on a desktop, and JavaFX uses a scene graph. You sometimes need to think a little bit carefully about that. So Gerrit, who's sitting at the front here, I was watching one of his presentations a couple of months ago, and he was talking about JavaFX on embedded and said that you need to keep the scene graph reasonably small to avoid overloading the way that the system works. And so ideally less than 50 nodes. Certainly I found that in the application I've written, I've not run into any problem of having too many nodes, but then I've kept the UI fairly simple. So it would be interesting to see what happens if I started making it more visually appealing, shall we say. Right, so let's talk about how we build a Java-powered Carputer. So firstly, what were the design objectives that I had for my Carputer? Well, what I really wanted to do was to display more information than I could get in the car at the moment. So obviously, if I'm driving the car, I can see the speed, I can see the speed of the engine, I can see how much fuel I've got left, and I can see the temperature of the engine. But that's about it. So I thought it'd be interesting to see if I could get more information and then display it on the screen. So maybe I can get more information about the engine performance, real-time power, real-time torque, engine load, those kinds of things. Also collect driver data. So I could see, you know, what's the throttle position, steering angle of the car, the braking forces, that sort of thing. And sort of related to that, the idea of G-forces on the car. Because I thought that would be quite entertaining to see as I'm going around a corner, just how many Gs am I pulling? Well, or less than 1 G maybe. But also quite interesting to see what my driving style is like. And same idea, recording the data for later use. So see what's going on, play it back and say, okay, you know, you're going around a corner here, you lost control, or I didn't lose control. That kind of thing. Playing at Formula One, certainly if you follow Formula One, you get a lot of telemetry from there and seeing what's going on. And I thought, you know, maybe I could even improve my driving style. Not that I need to improve my driving style, because sharing the same view that almost the entire human race has, I'm a better than average driver. Anyway, in order to get the information, as I say, there is this service port underneath the dashboard of your car that you can plug something into. And if you go on eBay, you can find these little boxes which are available, which are typically called an ELM327. And that's the name of the chip that's inside them. What they do is they plug into the service port, and then they talk to your computer, to your car, I should say. They also talk to your computer via either Wi-Fi or Bluetooth. So in the case of the Wi-Fi one, they make like a little Wi-Fi hotspot with an IP address, and then you can communicate to that with wireless communication. Or if you want, you can use Bluetooth, and then they do Bluetooth communication. For what I was doing, I decided the Wi-Fi one would work better. So essentially what I did was plug it in, get the IP address, and then set up my Raspberry Pi. So I had a Wi-Fi dongle and connected on the same subnet and got everything working. Pretty easy. Change the etc. network interfaces, set up for ad hoc networking because it's just point to point. There's no router, there's no switch involved, and fixed IP address. So pretty simple in that respect. Once you've got that, you can then obviously open a port to the connection on the ELM327, and you can send signals to it, and you can get back data. And the way that works is that most of it you send in the form of AT commands, for those of you who are old enough to actually remember modems and being able to control modems. So you can send AT-style commands. If you send non-AT-style commands, then you can actually communicate directly with the CAN bus, and you can send signals to say, you know, this button's been pressed, or change the channel on the radio, that kind of thing. From the point of view of the Java coding, pretty straightforward. It's, you know, simple networking, open a port, write a sequence of bytes, read a sequence of bytes, and that's about it. The other thing I wanted to do was to have some kind of display. So I needed a touch screen in order to control the interface. And again, I went onto eBay, and I found there was a company that was selling these touchscreens, which were really purpose-built for in-car systems. So this comes in what's called a 2-DIN fitting, which is basically a double height for the old-style radio and CD players, and would fit into your center console. It runs off 12 volts, which is very handy, and it's got an HDMI connector. So they actually sold it as being suitable for connecting to a Raspberry Pi. The other thing it has in terms of the touchscreen is a USB connection, so you could plug that into the Raspberry Pi and then get the information about where the screen was being touched and interact with it that way. Which leads us to one of the issues that I had in terms of getting this whole thing working. So I plugged in the touchscreen, I got the display to work, and I tested it with the Raspberry Pi using the X desktop, and I could control the X desktop with the touchscreen, and that all seemed to work. When I tried to use it with JavaFX, nothing would actually generate any events, so I was like pressing the screen, and it was a bit like the demonstration this morning when Stephen was trying to get the screen to work, and then you try pressing it harder and harder. And this is this concept that the harder you press, the more it's going to feel it, so it's actually going to respond. Obviously, it doesn't. So what I discovered was that when you plug the device in and you look at the messages coming from the kernel, it does actually recognize it. So it comes up and says it's an eGalax device. That's great. And it creates a couple of entries in the /dev/input directory. So it creates event 0 and event 1. And I spoke to the engineers who were working on JavaFX for embedded, and they said, oh yeah, that should work, because we take all the events from event 0. And we ran some tests, and they gave me some sample code and things like that. And we discovered that it was not sending any messages to event 0. It was all sending them all to event 1. So they said, well, we can do a special build of JavaFX where it'll look at event 1. And I thought, well, there must be a simpler way of solving this problem. And so I came up with the idea, well, okay, let's just delete event 0, and then we'll recreate event 0 with the same major and minor device numbers as event 1. And we'll put a little script at the startup, the boot sequence, and lo and behold, everything works. So now my touchscreen works without having to have a special build of JavaFX. But it was nice to be actually able to solve that. So this is the very complex architecture that I came up with in terms of the device itself. So we've got the touch screen, which is the display and the input. That connects to the Raspberry Pi, both through the HDMI and USB. The Raspberry Pi communicates with the ELM327 through a USB Wi-Fi dongle. There's also a converter for the power, so I get the 12-volt power from the car, run that through the converter, and then you get 5 volts that actually powers the Raspberry Pi. The other thing I decided to add to this was an accelerometer. If I want to measure G-forces, I need an accelerometer. So I added one of those as a SparkFun board that you can get, which has a 9 degrees of freedom accelerometer. It's the same one they used in the Duke pad. And so you've got acceleration in 3 axes, you've got gyroscope in 3 axes, and you've got a compass in 3 axes. So you'll see now that I've got the box at the front here, and this is the sort of inside of the box, which you can see has some of my kind of design in it. I'm a firm believer that any good software project should involve woodwork. So I had to have some woodwork in there somewhere, so there's some pieces of wood to hold the screen in place. The other thing you'll notice is that I had some difficulty sourcing a short HDMI cable. Hence the 1 meter cable, which is kind of looped around a few times and then sort of stuck in. It would have been much better if I'd found a shorter one, but it worked, so I was okay with that. That was fine. Talking a little bit more about the accelerometer. So as I say, it was a SparkFun breakout board, uses this nice little sensor, which has the 9 degrees of freedom. Also built into that, it's got some processing power built in, so it can take the combination of signals from the different sensors and give you some quite precise sort of positioning data if you want to use it for other types of applications. From the point of view of communicating and getting it to work with the Raspberry Pi, it uses I2C, which is a well-known and very common way of connecting sensors to computers. From the point of view of getting that to work with the Raspberry Pi, it wasn't too difficult. You basically have to make sure that the right modules are configured. So you have to download a couple of modules and then make sure that they're actually configured into the kernel. And then you've got to detect which address on the I2C bus it's using. And so you just use I2C detect -y, 1, and that gives you the address. The one thing I didn't quite get working was the compass, because that had a slightly more complicated way of communicating with it. And because I was trying to get this ready for Java 1, I sort of said, okay, well, let me get the first bits working, and I'll come back and look at the compass later. From the point of view of some code, I used Py4j, which is a great API, because I was using Java SE embedded rather than ME. If I'd been using Java ME, I could have used the device access API. But because we haven't got that running on Java SE embedded yet, I used the Py4j library. And that's a very simple API, covers all of the things that we want to be able to do. So you just get a reference to the I2C bus. Then you have to tell it what device you want to talk to and its address. So that's the OX68 highlighted in blue. That's what you get from doing the I2 bus detect. Then you've got to send a couple of messages to the sensor basically to set it up, because the accelerometer can measure in sort of 2, 4, or 6G. And I figured my car was probably not going to be pulling 6G going round a corner. I hope it's not. It's certainly like 6G braking. That was like driving it into a brick wall, really. So you set up the gyroscope, you can set up the accelerometer, and then you basically just read packets from it. And the format of the packets is defined by the documentation, and you can extract from that the acceleration data X, Y, and Z. One of the things you have to do is you have to compensate for gravity, because an accelerometer will measure gravity, because gravity is an acceleration. So as I've said here, the Earth sucks. What this means is that you have to take into account the fact that gravity is a constant. We definitely know that. Maybe if you get into advanced quantum physics, it's not quite constant. But for our intents and purposes, it is constant. But you then need to filter that out. So you need to filter out gravity as the Y component, if you like. We also have to assume that there will be no rotation involved, which is not strictly speaking true, because as you go around a corner, the car will actually lean a bit, and if you brake or accelerate, the car is going to pitch a little bit as well. So I didn't bother going into all the details of trying to take the information from the gyroscope and then feeding that in and trying to compensate for it, because, let's face it, I wasn't looking for an absolutely 100% perfect answer. I just wanted a demo that worked. So like I say, you could integrate the gyro. There's a thing called a Kalman filter that you could do for higher accuracy, but I haven't done that. If we have acceleration information, we can then, from some other information, calculate the torque and the power that's being generated by the car. So in terms of the torque, what you do is you take the mass of the car, you multiply it by the radius of the wheels, and the acceleration in terms of g, and that will give you your torque in Newton meters. And then if you want to convert that into the good old imperial units, which we in the UK use, then you get torque in Newton meters times a conversion factor of 0.73756, and that gives you pound-feet of torque. And then if you want to also get the power in terms of brake horsepower, you can take the torque in pound-feet, multiply it by the engine speed, and divide by 5252. You have to look this up on the internet. I didn't figure this out for myself. And you get the bhp that your car is generating at a certain point. And then, obviously, because we're relying on the acceleration values and various other things, we're not going to have an exact number. So it won't be 100% perfect. The mass is not going to be precise, because, okay, I can take what the manufacturer says the weight of the vehicle is going to be. I know roughly how much I weigh, but then you've got how much fuel there is in the car. You've got, like, if you've got any extra bits and pieces in the car, then there's a little bit of variation there. The wheel radius is not going to be precise, because, of course, you know, you've got a tyre which has, like, air in it, so it will actually change its radius slightly as you move it round. And then the acceleration, because we're obviously not using precise data because we're not accounting for the pitch or the roll, then we won't get an exact number. But it would be interesting to see if we could get anywhere close to what we expect, and to compare it against the manufacturer's figures. In terms of the design of this, what I wanted to do was to get sort of real-time data. So I needed some sort of screen-based design which would show various bits of information. And so I came up with the idea that we'd have different screens for showing basic data, for showing advanced data, the G-forces, maybe graphing some of the results so we can see how things change over time. And then we need a simple UI, because what you don't want to do is have lots of text and lots of numbers where you have to look very carefully at it as you're driving along, because that's not a good recipe for continued driving. Similarly, in terms of making sure that you can control it very easily, using a touch screen and not having to select that particular icon to get the menus pulled down to then select that particular option on the menu, again, not a good idea for driving safely. So then I thought, well, let's look around and see what other people have done. So let's take some ideas from inspiration from other places. So this is the kind of display you get in a Renault Megane Sport. The one on the left is a slightly older version, the one on the right is a little bit newer. So the one on the left shows you boost pressure for the turbo, it shows you the throttle position, shows you torque and power. The one on the right has got this nice little sort of display that shows you the G-forces that have been involved in your car as you've been driving around. And then you can take things a little bit further. You can look at something like the Tesla. And I was lucky enough to actually get driven in a Tesla this summer. And it's got this like whacking great 17-inch, it's like having a MacBook Pro on its side in the middle of the car. And it shows you all these pretty pictures of what's going on and what's happening, and enabling you to change the radio channel or things like that. So that was probably going to be a little bit beyond what I was aiming for. And then you can take it to even more extreme, and you can look at, well, what do Lamborghini do? So this is more like the display you would expect from like an X-Wing or a Viper, for the Battlestar Galactica fans amongst us. So they've got this kind of weird display here, which shows on the left you've got the tachometer, and it kind of, for some reason it uses two values, and then the idea is that as you accelerate it moves up, and then as you change gear then it moves the middle thing up and just displays things. And you've got a couple of sort of normal gauges, and then you've got this thing on the right which I don't actually even have any idea what it does, and the thing in the middle which again must be something to do with G-forces or something like that, some special Lamborghini thing. So this is what Lamborghini do. This is what I did. Came up with a slightly simpler approach. Well, as I said, you want to keep the number of nodes in your scene graph fairly simple, and I want to make it clear and easy to read. So I basically came up with the idea of showing a value using a bar chart. And rather than using the bar charts you can get in JavaFX, I used one that I built myself. Three nodes. One for the outer rectangle, one for the rectangle that shows you the value, and then I put a red line so you could see the highest value that had been acquired so far, and then you've got optional labels, which would be a couple more nodes in your scene graph. But it's easy to understand, it's easy to see what's going on, and it's easy to program. Then in terms of the user interface, already talked a little bit about this in terms of not wanting to distract the driver. You want to make it simple. So the approach I took was to say, okay, we've got a sequence of screens that will show different data. And rather than having to select which screen we want, we'll simply say that whenever you touch the screen, you simply move to the next screen and we'll just loop through them so you can easily select what you want. Very simple. You set all the components to have set mouse transparent, and then the mouse events are pushed all the way to the back, and you just have a rectangle at the back that you can pick up the mouse event on. I did also want to use the steering wheel buttons using the CAN bus data, but again, I ran out of time. And one of the downsides of using the CAN bus, aside from if you start writing to it, is that for some reason, the car manufacturers are not keen on sharing the information about what goes on the CAN bus. So you basically have to reverse engineer it yourself, which I haven't had time to do. So these were the screens that I came up with. First of all, I wanted a splash screen. I wanted it to be a splashy splash screen. So what I did was I took a picture of the satellite navigation system, the MMI system that I've got in the car at the moment, and then overlaid the Java logo and Duke with a Raspberry Pi, so I could have a more Java-focused one. The next screen is your basic data. This is just taking information from the EOBD2 protocol. So you can see the engine load, you can see the air temperature on the intake, you can see the catalyst temperature, so that's the exhaust on the output. You can see the throttle position, and you can also measure or get a reading for the fuel pressure, so you can see how much fuel is being pumped into the engine. Then for some slightly more advanced data, I took the throttle position again, added the engine speed so we could see how fast the engine was going, and then using the accelerometer data, calculate the torque and the power so we could see how that was varying over time. Next screen was to show the G-force, and who follows Formula One here? Yeah, a few people. So if you watch Formula One on the TV, you'll notice that this looks quite similar to what you get on there, and they show the telemetry of as the Formula One cars go around the track. And so basically, depending on how far the dot moves in particular direction, that shows you how much G-force you've got. Now, this is a bit of a fake screenshot, because if you notice, the yellow dot is is not at 0, but all the values are 0. But essentially what you do is you say, okay, left and right is easy, because as you're cornering, you get G-force laterally. Up is the G-force as you accelerate, down is the G-force as you brake. And then the line on the right-hand side is I just added in the G-force so you could see as you're going over a bump or a sleeping policeman, and you would see the G-force going up and down like that. As I say, the other thing that we want to do is record some historical data. So I thought, right, well, let's put a graph in which shows the throttle position over time, and then you can see how much is going on, and you can sort of track that. But I'll show you that in the example later on. One quick bit about JavaFX and charts. What I had to do there was I had to use CSS to style the chart, because it doesn't work very well if you've got a black background, so you have to change the colors of various things. So this is just the different things. You have to set the axis to be, in this case, white. You have to set the tick marks, the minor tick marks, the plot background, alternative row fill, and things like that. So that was just setting the JavaFX so that it would work well on a black background. In terms of the design, I did actually have a design. I didn't just throw it all together. So I came up with the idea that you'd have a sensor interface, and then there would be different types of sensors that would work with that. So you've got the idea of the EOBD2 sensor, which is the sensor giving data from the car. There's the acceleration sensor, and then using that, I thought, well, okay, let's have the case where we've got the real data, but we could also then have the idea of simulated data, or we could connect something and actually replay the data from a run in the car. So you end up with a simulation car, simulation accelerometer, and that kind of thing. And then you've also got the idea of the engine performance, which is a kind of combination of different pieces of data. Design side, as I say, it's just a sequence of screens. So we start off with the idea of a display, which is the standard screen that we're going to use, and then build on that to give you the basic display, the advanced display, graph display, then further subclass. So you've got different types of graph, whether it's a throttle, power graph, and so on, and also the G-force display. So just a simple design. And then putting the two together to get your controller, good old model view controller design, we end up with a situation where we say, okay, for each screen, we just read the data from whichever sensor we're interested in. And by using the interface, we can use polymorphism, and then if we want to change from using a simulation to the real data, it's just a matter of switching the value or the object that we pass to the display in terms of actually getting the data. Just a little bit more about CAN bus. As I say, I wanted to use the buttons in the car to say, okay, rather than touching the screen, let's use the steering wheel buttons and say what is going to happen. But as I said, the manufacturers are not keen on sharing this information, so what you literally have to do is sniff the data that's coming on the bus and read all the signals, and then try and figure out from all the massive data that's coming on the bus, when you press a button, what's the address of that button and what's the value that it sends, and then you can replicate that with your code. But as I say, I didn't actually have time to do all of that. So a couple of things about some future ideas I've got, some conclusions, resources before we do the demos. I've got a number of ideas for things to do next. So one of them I thought would be really good is to add a heart rate monitor. So as I'm driving, I can kind of coordinate, or I can see how the G-forces relate to the pulse rate of the driver. Clearly integrating some sort of GPS receiver would be interesting, because then you can plot a map and you can see the car data based on the position of the car. Other thing I've got as quite an interesting idea is building a heads-up display, because some cars nowadays actually have heads-up displays. So I've got one of these micro projectors that you can get, and I've also got some sort of half-silvered plastic. So my idea is to sort of like put this in the car and then have a heads-up display so that I can see what the data is without actually having to look down from the driving. Other things that we could do with CAN bus, trying to figure out what the brake pressure is, steering position, those could be useful things, using other switches, and then the idea of sending commands to the car, which it's a lease car, so I'm a little bit hesitant about doing any real surgery on it. Another thing that I found is there is a little board that plugs into the Raspberry Pi called the PiCan. And what that does is it enables you to talk directly to the CAN bus rather than having to go through the OBD2 port and using the ELM327. So there's a little board. If you take the satellite navigation out, you can then wire directly into the car's systems and do it that way. But as I say, because it's a lease car, they may frown upon me soldering the car. Places to go for more information. Obviously, I've got an Audi, so you can have a look at audi.com. RaspberryPi.com, there's lots, or raspberrypi.org, I should say. There's lots of forums there, lots of really useful information, JavaFX.oracle.com. And I've also got my blog where I've written a number of blog entries about this so far. And I really do need to sit down, hopefully in the next couple of weeks, and write up a sort of a finishing report on what I've done with this to show how it actually works. So I've still got 10 minutes, which is good, because I can now show you some demos. So, as I say, I don't have a car with me. So what we'll do is I'll show you a video of the box in action. Now, I will have to apologize in advance for the quality of the video, because it was very difficult for me to find a professional videographer. So I had to rely on my friend, who's not professional, as you'll see. So there's no real sound to go with this. So this is basically, let me see if I can put that in full screen mode. Oh, no, where are we? Hang on. There we go. So this is just, there we go, right. So you can see the box is mounted on the top of the dashboard. And then I've used some big blobs of blue tack to hold it onto the windscreen, because otherwise it tends to move about a bit. But basically here what you're seeing is we're just driving around a roundabout or off a roundabout. That's just showing basic data. Don't worry about the fact it's a little bit shaky. I'll show you in a little bit later on. So it's not too long, it's about 3 minutes. So, okay, so now we've got the G-force data. Now there's a roundabout at the end of the road. This is by the Oracle office in the UK. So there's not much traffic. But what we'll do is we'll go around the roundabout and we'll see each of those lines represents 0.5 G. So if we manage to get it all the way across, it's 2 G. But I think we managed to get nearly 1 G going around the roundabout, which is probably why the camera was a little bit shaky. And then we came back off the roundabout. So we go back. Yeah, now, does anybody spot the error in my code here? So there's a bit where the throttle position seems to dip below 0. So I found out that this is because I don't really understand signed versus unsigned numbers. So I've had to go back and change that in my code. But I have fixed that since. What are we doing now? So yeah, there's the G. Oh, that's right. We were going to come off the roundabout and then we're going to try and see whether we could get some acceleration, see what G-force we could pull in the acceleration. Gets a bit blurry. So it managed to just over half a G going in the acceleration, and then we're waiting at the roundabout, so there's not much happening here. And then we'll just sort of move off, and I think there's probably not much more to that. I might actually end it there, because what's more interesting is if I do this. I don't think think I need to go to that, do I? Right, so on here, now, can we have the camera zoom in on that? Hopefully this is still running. Let me just check on here. Right, so what I did then was, as I did that run, the code also wrote all of the values from the different sensors into a file. So just as a comma-separated value list. And then I wrote a little playback server so that I could make the laptop behave like the car, and so simulate the data. So now that's sitting waiting for the... Yep, good. Okay, so if I run the application on here, what should happen is it'll take a few moments because it does take a little while to start everything up. But that's brilliant, yes, because you get a much better view of the screen there than you did in my video. So it's running in simulation mode, and it's going to connect to the remote socket. That's fine. And then it'll go into the splash screen, and then it will actually, there we go. So we displayed the splash screen for a couple of seconds, and then what we'll see is the values. So that's basically the values you were seeing on the screen. Now, if I use the touch screen, for some reason it doesn't actually accept the first touch, but then if I touch it again, we'll switch to the second one, so that's the advanced data, which is showing the torque and the power output and so on. And then if we go to the G-force display, you'll see that we're moving around, and we've actually got the values as well as and the idea of the green blobs is to show the maximum value that we got in each axis. And so that's kind of interesting. And then if we see the throttle position, and that sort of runs a bit. So it's surprising, actually, when you drive around, you find how little you use the throttle most of the time. And then you find, okay, so, well, let's see, I'll give it a bit of a bootful, and then suddenly it's like, where are we? Go on. Any moment now. There we go, yes. Obviously, I was accelerating hard at that point. And similarly, if we look at I've probably not got this graph scaled correctly, or my values are not being generated correctly, but you can see the peaks as the actual power output is being generated. So, and then I had to have some way of getting out of the application because the Control C didn't work, so I had to have like a big button that would actually enable me to get out of the application. So essentially, that's what I did, and it was, like I say, it was a lot of fun to do this, but I think there's also a lot of real sort of things that are actually relevant here in terms of applying Java to this kind of thing. We've certainly been talking to some car manufacturers about this kind of thing, and there was somebody who came up to me after a session earlier on and was talking about the same thing. So there's a lot of interest in combining computing with cars. So with that, thank you very much. Since I actually find myself with 4 whole minutes left, if anybody's got any questions, I'll take those. In front. Right, yes, a very good question. What about security issues with accessing the system? This is one of the significant things about this, because there are no security protection on this. If you plug something into the OBD port, there is nothing that stops you from reading or writing data to and from the CAN bus. They rely on physical security as the way of preventing people from doing that. So in theory, you see, if you have one of these things plugged in and somebody is outside your car and knows that it's plugged in, they could then connect to it and actually override signals and do things like that. So it is something which is of a concern to a number of people about that kind of thing. Any other questions? Yeah. Was it hard to decode the data? No. In the case of the data I was using, because it's under what's called OBD2, and that's a European standard for making sure that your car's emissions are monitored. And so that information is actually very easy to extract. So engine load, engine temperature, RPM, things like that, very simple to extract. It's the CAN bus where you want to get things like the controls and controlling the hi-fi or the satellite navigation. That's when it gets complicated. But the basic values are very easy to extract. Yep.
If Oracle ever decides to leave the database business and commercialize this product, I mean, what would their hardware options be besides the Raspberry Pi?
Okay,
I mean,
yeah.
they wouldn't use the Raspberry Pi.
No.
And what would the impact be on the code which has been written for this?
Right, very good question. Okay, so if you were going to do this commercially, you wouldn't use a Raspberry Pi, and that's absolutely 100% true. One of the things that's complicated with building car systems, if you talk to people like Bosch, who do a lot of in-car electronics, is you have to have certified hardware. So it has to be able to withstand very high temperatures, it has to be able to work in low temperatures, it has to be able to work in conditions where there's a lot of vibration, those types of things. So you basically have to design a specific board that would be then certified and able to work in a car environment. So that would be the sort of thing you would do. But the great thing about, from this kind of software's point of view, is that because it's Java, you don't care what the platform is that it's running on. So even if you wanted to change the architecture from using an ARM, you could choose like a different ARM processor and go for like a more modern ARM v7 rather than the ARM v6, and you wouldn't have to change any of the Java code. And so that's the value that we have from Oracle's perspective, is that by using Java, you've got the right one to run anywhere, and you don't have to port your code to different platforms. Another question? Yeah.
How hard is it to make the same thing work on a mobile phone?
It's actually very easy, because if you go on eBay and you buy one of the... So the question was, how hard is it to make it work on a mobile phone? Because it is just either Wi-Fi or Bluetooth with the ELM327, if you go on the App Store or Google Play, you'll find that there's actually several applications that have already been created that work specifically with the ELM327. So you can take a mobile phone, you can stick that on your dashboard, it will give you some of the different types of data that I've got, and you can get that for like 69 cents or whatever. So there are applications already available for mobile phones. Yeah. Any other questions? I don't see any other questions. Oh, no, one more.
Yeah, one quick question on the data that you're capturing. So you said that not everything is documented in terms of OBD, right?
Right. Well, OBD is documented. It's the CAN bus, yeah.
To what degree can you reverse engineer all of this data and use it in a commercial application? Focusing the vendors on?
Well, there's nothing that would upset the vendors, because it's available data, so you can extract the data. All you have to do is try and figure out what the mapping is between the address that they use and the value that you get from that. So it's possible to reverse engineer it, because certainly if you search on the forums and things like that, lots of people have actually tried doing this. So there's little bits of information where people have managed to reverse engineer it. And in fact, some people have been quite successful with this, because there was one example where somebody was selling some hardware that would use the driver information system, which is the little display in the middle of the dials on an Audi. And it was an older one, so it was just monochrome. But they could actually write pixels to it, so they could actually draw pictures on the driver information system. So it is possible to reverse engineer it and use that data. Yeah. Okay, I think I've run out of time, so as I say, thank you very much.